Howdy, my name is Elijah Ricks. I'm an associate professor of forensic psychology at a private university in Chicago, and I also teach statistics. I decided to make a little video about working with the correction for Cramer's V. Cramer's V, of course, is a measure of effect size for contingency tables that are larger than 2 by 2s. However, it has a few issues with it, and so I decided to make this video to kind of explain that for those of you who are interested. So, of course, I'm sort of assuming here that you already know how to calculate a chi-squared value. If you do not, I do have some tutorial videos. Of course, other people have made some as well. I also provide a calculator that is not my own, but a link to a calculator in the description of the video, so feel free to use that. But of course, after you have that chi-squared statistic, there are several things that you may do. There are also some things that you should do. I recommend Sharpe's reading there. I've also provided that in the description of the video for a fairly straightforward review of what you should probably do and what would be most appropriate for your situation. Now, of course, for most statistical analyses, it's appropriate, and in fact, maybe there aren't exceptions, but you really should calculate a measure of effect size, which of course tells you not only whether it was statistically significant, which you should already know by then, but what was the impact of one variable on the other? What was the size of the magnitude of the influence of one variable on the other? And so that's what we can do here. Now, typically, if you have a 2 by 2 chi-squared, you use phi as the measure of effect size. It's pretty standard. However, if you have a larger table, for example, you have 2 rows and 3 columns, or vice versa, or a 3 by 5 or a 9 by 2, or whatever you're doing, the phi actually is typically inappropriate, and so we use Cramer's V instead. Cramer, of course, was the person who came up with the statistic. And it looks like this. Of course, as you can see, it's very easy to calculate. All you do here is you take the chi-squared value that you already obtained by this point, obviously. You divide it by the total number of observations you have within the chi-squared contingency table, and then you multiply it by whichever is less, the number, or I should say fewer maybe, the fewer rows or fewer columns, and then minus 1. And then take the square root of that, of course. So it's very easy to calculate and straightforward. So of course, however, it has some problems, which is why I'm making this video. And this, again, was not my idea. This, of course, goes to Bergsma. I provided the link to his article also in the description of the video. Bergsma, of course, demonstrated that Cramer's V tends to be biased. And in other words, it tends to overestimate the size of the effect if a table is especially large or if it has a small sample size or both, of course. So if you have relatively few observations in the contingency table, but a lot of rows and columns, it tends to overestimate the size of the effect. Now, I say, large rows or large columns doesn't necessarily have to be that many. In fact, I'm going to give you a demonstration of one that has just two rows and 3 columns, so it doesn't have to be that large. The issue in my example I'll give you is, of course, a small sample. So, as he demonstrates in his article, I don't need to go into that, it usually outperforms, in terms of accuracy, the size of the effect, outperforms Cramer's V traditionally. Here's the equation that he gives. This looks like a lot, of course. I'm going to give you a simplified version, one that is probably easier to work with for most people, especially if you're relatively new to statistics, if you're a student, that kind of a thing, or you just typically don't like all these symbols. So of course where this is going on, and again, I'll explain all this easily. So you can see the R with a little squiggle and the C with a little squiggle, and this of course is the phi with a little squiggle. I'll walk you through all of this and we'll make it more usable. This is the separate equation to figure out R with the little squiggle, and then a separate equation to figure out C with the little squiggle. All this is very important though, and so I'm going to give you an equation that I've come up with. It's mathematically equivalent, and it's not an equation that I came up with. It's just sort of a version of Bergsma's that I find a little easier to work with. So I'll show you how to work with that. Right, so let me show you the formula we've got here. This is the one that I've come up with, but again, it's mathematically equivalent to Bergsma's. Okay, so again, we've got two decisions we need to make up here in the numerator. We first have to decide if we're going to use the value of 0 or if we're going to use the value that we come up with over here. Now, it usually will be the value that you come up with over here. Basically, another way to think of this is that you can't have a negative value up here. So if anything, you're going to get 0, and you'll just use 0, and therefore your effect size will be 0. Or you're going to have a positive number. So the point here is that it cannot be a negative value up here because you can't take the square root of a negative value. So hopefully that's clear. Anyway, so it'll almost always be whatever's in here. And we'll just fill it out and then make sure that it is larger than 0, of course. And then down here, we also have to choose, are we using the columns as the reference point or the rows as the reference point? It's simply whichever is fewer. So if you have 2 columns and 3 rows, you would, of course, plug in the number of columns instead of rows. In our example, I'll show you what we'll do here. Now, once again, I'm assuming that you already know how to obtain this chi-squared value, the chi-squared statistic. If not, of course, make sure that you figure out how to do that before you just start doing this. And of course, n, the capital italicized n means the total number of observations that are in your table, the total number of observations of your contingency table. So now let's look at an example here. And these are just made up data. I want to make that absolutely clear. This has nothing to do with anything. Um, Obviously, you would want to be very careful about the research methods, and you want to make sure everything's valid and reliable, and was there random assignment, and all that kind of stuff. So that's really not germane to what we're going to be doing. So just assume that this is the data that we're working with. Now, in this made-up example, what we've done is we've taken 3 different categories of marital therapy. We're trying the typical conventional marital therapy for couples who are considering divorce, a new therapy that this researcher has come up with, or whatever this theorist or clinician has come up with, and then couples who didn't receive any therapy. And we're trying to see if there's a difference in the likelihood of getting divorced or staying married, depending on which therapy you received, of course. Okay, and so as you can see, for example, let's see, what is that? 21 people, 21 couples, I should say, received the conventional therapy. 8 of them got divorced after, by the way, this is after 6 months or something, we'll say. And then 13 of them stayed married. So again, just for the purposes of argument, let's imagine these are real data. Now, of course, you can do the math and check this out, but of course, there are 59 observations, meaning there were 59 couples in my research here, this made-up research. So let's imagine there's a relatively small study, or at least you had fewer resources maybe to spend on couples. And then the chi-squared value for these data is 6.107. Okay, so again, you can do the math and check that out. By the way, if you find something different, please do let me know. Sometimes I make mistakes. Anyway, so let's first calculate Cramer's V traditionally, and we'll see what that looks like, and then I will show you how to calculate the correction for Cramer's V, because again, we have relatively few observations. The table's not especially large, but relatively few observations, which makes me a little nervous about whether we're getting the correct value of Cramer's V. So in the traditional method, of course, we plug in the chi-squared value, as I said. The chi-squared statistic in this case is 6.107. Just make sure that you're not re-squaring it because it's already squared. The chi-squared statistic is called chi-squared because it's already squared, so you don't need to re-square it. Just plug it in, 6.107. The n value, of course, the total number of observations we had in my little example is 59. And of course, we had 2 rows and 3 columns, and 2 is, of course, fewer than 3. So we're going to plug in the value of 2, and of course, take away 1. So of course 2 minus 1 is 1, 1 times 59 is 59, 6.107 divided by 59 is 0.1035, the square root of which is of course 0.3217. So the Cramer's V value of effect size is 0.3217. We can interpret that, of course, we'll get to that at the very last end of this. But of course now I want to show you what we would obtain if we use the correction for Cramer's V. Okay, so here's again the equation that I've already showed you. Now I'm going to, in this case, we're going to get rid of this one because we had 3 columns and we had 2 rows. So I already know we don't need to use this. I'll just take that out of the equation. And we'll just use the rows down here. Nothing else is different about the equation, however. Okay, so now we simply need to plug in all of the values where they go. So here again is the equation that I already had, and now I'm going to plug in the values that we know. Our chi-squared value was 6.107. Our value of n, of course, is 59. We had 3 columns, so 3 goes right there. I'm going to subtract 1 as it says. We had 2 rows, and so I'm going to plug 2 in right there. Again, n was 59, so 59 is going to go right there, and as you see, it says to subtract 1 from it. Then down here, again, we had 2 rows, so that goes there, and 2 goes there as well. Again, 59 goes right there. Everything else should be the same. The minus 1s go there. I'm going to square that difference right there, and of course, minus 1 there. Okay, so now all we do is simplify the equation. So I've simply moved that equation right up here so you can see what I'm doing. Of course, I'm keeping that in because I don't know yet if I'm going to get a positive value in here, so we'll just keep going on with that. So 6.107 divided by 59 is, of course, 0.1035. By the way, I'm rounding out only to 4 decimal places. You can, of course, do more. I generally recommend rounding to at least 2 decimal places to my students anyway. 3 minus 1 is, of course, 2. 2 minus 1 is 1. Okay, and 59 minus 1 is 58. Again, nothing very difficult here. The real challenge here is just making sure you're keeping track of what you're doing. Let's see, 2 minus 1 is, of course, 1, and 59 minus 1 is, of course, 58. So far, so good. Now I'm going to continue on the next slide. As you can see here, same thing. Up here, we can't do anything except the 2 times 1. So 2 times 1, of course, 2. That'll go right there. Down here, we can divide 1 by 58. 1 divided by 58 is 0.0172. And of course, everything else stays the same, step by step. Now we can solve. We'll take 2 divided by 58 to get, of course, 0.0345. And of course, it rounds out even more than that. Or it goes out more than that. So then we're going to subtract those in just a moment. Let's finish up the denominator, however. 2 minus 0.0172 is, of course, 1.9828. Then we're going to subtract 1, and we get to, of course, 0.9828. Of course, the difference between these two, as you can see, is 0.069. We divide 0.069 by 0.9828 to get 0.0702, and of course we still need to take that square root. The square root of that is, of course, 0.27. Now, as you'll recall, Cramer's V was 0.32, whereas the correction for Cramer's V is 0.27. So again, we did see that Cramer's V actually did overestimate the effect size, whereas Bergsma's correction made it more realistic. And as again, I have no reason to believe that Bergsma was incorrect about his suggestion that the correction was usually superior to Cramer's V generally. Now, in interpretation, of course, Cramer's V is a measure of the association between the variable 1 and variable 2. And so in some ways, it's like a correlation coefficient. One thing to keep in mind is that Cramer's V cannot be smaller than 0, and it also can't be greater than 1. It can't be smaller than 0, of course, because the very last step is to take a square root. And of course, the square root, you can't find a square root of a negative number. So Cramer's V definitely has to be 0 or positive, right? And it can't be larger than 1. So if you find that you got a value that's larger than 1, you made some mistake. Now we interpret it a little bit differently based on the degrees of freedom we have. In this case, we had 2 degrees of freedom because, and if you're not sure how to do that, it's we had 3 columns, minus 1 is 2, 2 rows minus 1 is 1, 2 times 1 equals 2, and therefore we had 2 degrees of freedom. With 2 degrees of freedom, we look at our thresholds here to see how large the effect size is. And as you can see, for either case, we were below 0.35, and therefore we'd probably call this in the medium range. So you might say, well, wait a second, what's the difference? Because we still call it medium. Well, of course, the problem is when you start to get it to different thresholds, is this going to make a world of difference? People are going to die because you reported the wrong Cramer's V. Probably not, at least hopefully not, but we want to be accurate here. We statisticians and people who are concerned, researchers generally, really want to make sure that we're giving people accurate information. And so that's how that works. As you can see, we did find that Bergsma's V value, Bergsma's correction was superior, and you can see how that goes. So I hope that was helpful, and yeah, take care. I'll see you in the next video.